Welcome to the first lecture of 311 Analog Electronics course. In this first part, we will start a review of amplification with transistors. We will review our knowledge from 212, bipolar transistor operation, MOSFET operation, so on and so forth. And then we will learn how to design single transistor amplifiers. Then we will combine them to have multi-stage amplifiers. But before starting, let's think about the name of the course, analog electronics. Some of you may think that, we are living in digital domain, so analog is kind of like old-fashioned. In fact, it's not true. So analog electronics is a very important course. Analog electronics design is quite critical. The main reason is the world is analog. You design electronic circuits for processing some information coming from the world, like, sound signal, image, or let's say for biomedical applications like brain signals. And all these signals by nature are analog signals. And even if you want to process them in digital domain, first of all, you have to handle them by using analog, electronics. Similarly, if you want to give some stimulation back to the world, again, you have to get back into the analog domain somehow and transfer this signal into analog domain. So analog electronics is important in that sense, but of course, if you think analog and digital like um, daily consumer electronics, of course, like this digital clock is much more fancier than the analog clock. Okay, so yeah, but in electronics wise, it's not the same. Analog electronics is very critical. There are some basic differences between analog and digital. So let's learn them. Maybe you know them already, but it would be good to go over them one by one. For analog circuits, you are dealing with continuous valued signals like this sine wave in here. So this sine wave, the red one, is a continuous signal, and you have the data for every single time duration. In digital one, of course, depending on your resolution, you convert this signal into binary values. So for this 2-bit resolution, for example, you create like 4 steps and try to represent the same sine wave by this like 4-step blue version. Of course, it doesn't look like the original signal because you are losing some data. And by increasing the number of bits in here, by increasing the resolution, you will have more steps. Like for this 3-bit version, you have more steps, and because of that, the output digital signal or discretized signal looks much more like the original analog signal, sine wave. If you use, for example, like 12 bits in here, you wouldn't recognize the difference between the blue one from the red one because with bare eye, it is very difficult to notice the difference between the step heights. But whatever you do, how much resolution you use, you are not dealing with continuous valued signals in digital domain, but you are dealing with discretized signals. And this means that you are losing some data. I'm going to tell it later on, but even if you have the highest resolution, you still lose some data. Analog circuits are difficult to design because think about an op-amp. In an op-amp, there are like 12 or more transistors, and you have to design every single node potential and every single branch current very carefully. Any mismatch or any deviation from the design value may result in malfunction of the op-amp. So design requires more experience and more attention. But for digital circuits, the signals are either high or low. Even if it is current or voltage, that doesn't matter. You are either dealing with high voltage, low voltage, or high current, low current. So you don't need to deal with like very precise or high accuracy design issues. So digital designs are easier to design. For the analog circuits, since the real world is analog, you don't need any conversion. You just take the signal, process it, and give it to the output as an analog signal. So you don't need conversion. But for the digital circuits, first you have to convert that signal coming from real world or analog world to digital, process it, and then give it back to the analog domain by converting it to analog signals. So you need analog to digital and or digital to analog converters. Then why do we need to use digital operation? Because digital is easier to design. The circuits are much cheaper. For analog, design is more complicated. Systems are a bit more costly, and because of that, you don't want to play the signals in analog domain. For the analog signal or analog circuit, no information is lost. This is very critical, and I have some good examples for this. Because you have the whole information over there. Maybe it brings some complexity and difficulty in design, but you do not lose any data. Digital versions are simplified version of the actual design. You get rid of the redundant data so that you can process it in an easy way. And this redundant is somehow like a tricky word. It depends on where you are using, what the customer wants. Like think about a music player, for example, a CD player, and you want to record some concert, classical music concert. If you listen it with bare eye, you listen all the tones and you do not lose much more information. It's limited by, of course, like, uh, the ear condition, of course, but you have all the signals coming. When you rip it in an MP3 file, for example, depending on the resolution of that MP3 ripping, you lose some of the data. If the resolution is low, when you listen the same music, you don't feel the same. You don't enjoy it in the same way. You lose some of the signals. Even if you increase the resolution, okay, at some point your ear cannot recognize the difference between the actual music and the ripped off music. So some amount of information is lost in digital domain, and it depends on the resolution of your signal. But still, it can be problematic. For example, think about the like old movies. The old movies like taken in, let's say, 1950s or 60s. Still, we can watch them in high definition TVs because those movies were recorded by using analog tape cassettes. They have the whole information over there. Like 20 years ago, when we were watching them in 4:3 scale with low resolution. But nowadays we have high resolution TVs, and the scale is changed like 16:9. But still we can watch them without losing any resolution. It's still like nice. Why? Because they were recorded first by analog recorders. But think about the movies taken in 1990s. But of course, not all of them, but some of them. Those of them taken by digital cameras are not compatible with today's high definition technology. So when you are watching in them in high definition TVs, for example, the scales cannot be changed, the resolution is really bad, and you cannot recover it. It's much more difficult to recover the actual signal because when you record it by using digital cameras, you lose some of the information. So that's the critical thing. At some point, the information lost may not mean anything. It may not be that much significant, but at some point, it may become significant. So analog does not have that problem, but digital have. Another problem is when you go to the market, it is more difficult to find analog engineers. So analog designers are rare. So less number of designers available. Why? Because it's difficult. Like you cannot automate it somehow. But for digital circuit, there are really nice tools like VHDL and Verilog. So you don't need to even design it in transistor level. You just define the inputs and you just define the outputs. You give it to the computer. Computer runs the program, and ends up with the final tape-out version of that digital chip. And because of that, of course, analog designers are getting more salary in companies compared to digital designers. So like cons and pros. And digital circuits have much more flexibility because you are dealing only with high or low voltages. Like it's either 0 volts or 5 volts for a design, for example. So when you are carrying out that design from one end to the other end, even if you lose some voltage, that 5 volt may decrease down to, let's say, 4 volts, but still it's quite close to 5 volts. So on the other end, the person dealing with that can recognize it as still high. So like losses inside the circuit, like resistive losses, capacitive losses, may become less significant because high and low level or binary operation saves you. But for analog design, of course, this is a significant thing because when the voltage changes because of the losses, let's say, it may change the operation region of the transistor and it may result in malfunction of the whole system. So analog circuits are not that flexible. So I think, I hope I convince you to learn more on analog electronics design. But, I'm going to use the same table in 312 next semester to promote digital design. So like both of them are important. Both of them have their own application areas, but analog is not old-fashioned and still quite important in the market and in the science, of course. So throughout this course, we are going to learn how to design an amplifier, and we will see that like, each time you need to design your own custom-made amplifier. And at this point, you may ask, why do we need to do that? Like, amplifiers are studied in the literature for many years, and there are like standard amplifiers available in the market, so we can buy them and we can use them. Of course, we need to learn how these standard amplifiers are operating, but still, why do we need to learn how to design it? The reason is this: for each electronic circuit, there are different types of amplifiers, and the requirements for those amplifiers varies a lot. So one standard amplifier may not work for your own application, for example. Or if you are designing an IC, you may need to use many different amplifiers, and each amplifier may need like different gains, different frequency range, so on and so forth. So here's a good example. By the way, when you are dealing with electronics, of course, this is what you would end up with at the end, most probably. There will be a PCB and some components like op-amps, capacitors, resistors, so on and so forth. So these are tiny chips. And a common example, a stereo receiver. This is the radio that you are using at your home or in your car or whatever. So what we have in here is an antenna, of course, picking up the radio signal. And this internal impedance is 75 ohms. The signal coming in here is like a very small one, like in the range of tens of microvolts. And if this is an FM radio receiver, the incoming signal frequency is in between 88 megahertz to 108 megahertz. Okay, so your radio picks up the signal by the antenna, and the signal is very low. And if you want to listen this thing on your speaker, you need to amplify it, of course. But a bare amplifier does not work. You need to use some blocks. The first block should be like a low noise amplifier, for example, or RF amplifier. Why do we call it as RF amplifier? Because it operates in radio frequency. So you need to amplify this thing first at radio frequency. And amplifying or processing signal at this high frequency is really costly. You can think about it like a rule of thumb. If you are operating at higher frequency, your circuits are much more expensive because your filters should be at high quality, your system should work at very high frequencies. So it's very difficult and very costly. So the first thing that you should do is you need to carry the signal, the information, to a lower frequency so that you can handle it by using a cheaper circuit. For that purpose, what they use is a mixer. A mixer is basically a multiplier. So this mixer is multiplying. So this is a multiplier. Think about multiplying two sine waves. Let's say the end product will be two signals. One is at like omega 1 minus omega 2t, and the other one will be at omega 1 plus omega 2. Okay, so if you have, let's say, the first signal at 1 megahertz, the other one at, let's say, 0.5 megahertz, the output of this mixer will be at 0.5 megahertz and 1.5 megahertz. And you can use this information or this technique to change the frequency of the incoming signal. How do you do that? Let's say that you want to listen Radio Otto, which has the frequency of 100.3 megahertz, okay, 103.1 megahertz. So you need some RF filter in here, and this filter gets rid of all the other channels, but keeps only this Radio Otto frequency. But still, it's at very high frequency. You don't want to use your circuit at that high frequency because you want to make your radio cheaper and design easier. So you put, let's say, 100.3, let's say, megahertz signal in here. So when you multiply them, you will have two components, one of them 206.1 megahertz, the other one at 0.1 megahertz or 100 kilohertz. So the operation frequency is lower. So by using a filter, intermediate frequency filter, you get rid of this signal. And now you are operating at a very, very lower frequency compared to the incoming signal. So the circuit design is much more easier. The cost decreases significantly, and you're operating at intermediate frequency. Then you can use a better amplifier, IF amplifier, for example, intermediate frequency amplifier. By the way, the numbers that I'm using, I'm just like throwing out from my hat, but there are some practical frequencies. Generally, they want these intermediate frequencies at like 11.7 megahertz or like 455 kilohertz, 282 kilohertz, something like that. So there are some standards on that, but I'm just trying to explain the concept to you. So this IF amplifier is cheaper. This is expensive. So you cannot make much amplification at RF, but you can make more amplification IF. But at the end, of course, you want to hear the signal on the speaker of your radio, and this speaker has an internal impedance of 8 ohms, and of course it operates in audio band, like between 50 hertz to 15 kilohertz. So you have some audio amplifier in here, which operates at lower frequency, like this one, and which drives a low impedance load. Think about it. So the first RF amplifier is driving a mixer. Mixers have generally high input impedance. So this thing is driving a high impedance load. This IF amplifier is probably driving a high impedance load, but audio amplifier should drive a lower load. This may not mean anything at this point to you, but it's going to be more clear in the coming slides. So load is another factor in here. What kind of load you are driving determines the type of the amplifier. This is a very simplified block diagram, of course, and we need to add much more components in here. But what I'm trying to do is I just want to explain, even in such a simple system, we need to use like 3 different types of amplifier. One, the RF amplifier operating at high frequency, driving a low output resistance or low input resistance load. The input is low resistance input. The second one, operating at in the kilohertz range, let's say, it's driving a high impedance load, and previously it has like high impedance previous stage. The audio amplifier, let's say, driving a low load, operating at lower frequency, and so on and so forth. So the moral of the story is this. When you are dealing with these amplifiers, the requirements may change. They may operate at different frequencies like RF, intermediate, or audio band. It depends on the application. You may need different types of voltage gains. Like in the previous example, for example, you don't want a large gain from the audio amplifier, but you want large gain from the intermediate frequency amplifier. So high gain, moderate gain, or in some cases even like unity gain may require. It totally depends on the application that you are using this amplifier. And it's not necessarily voltage gain. In some cases, you want to amplify current, right? In some cases, for example, your input can be voltage, output can be current, or vice versa. So the type of the gain may even change. So type of the gain may change. And the other thing is different driving capabilities. So each amplifier drives a different load. So type of the load may change the design. For the audio amplifier, we were driving 8 ohm load speaker, a low impedance load. For RF amplifier, it was driving a mixer, which has high impedance. So this is going to make a significant difference in the amplifier design. So that's why we need to use different amplifiers. We need to use different designs. So in some cases, we may not use the standard amplifiers available in the market. For some applications, we may need to design our own operation amplifier. So this is a good example. Let's say that I want to drive a speaker. So let's say this 8 ohm impedance is modeling a speaker. Okay. And you have, let's say, you designed a source, which is a music player. But assume that this music player is lack of the audio amplifier at the end. So you buy the speaker from the market, you come to house, and you have this imaginary music player without the audio amplifier, and you want to hook up this speaker to the music player, and you want to listen to very loud music, right? If you do not use the audio amplifier, let's say that if the audio amplifier is not here, the circuit looks like this drawing. This RS models the internal impedance of the music player. When you hook them up, this is V out. V out divided by Vs will be equal to RL divided by RL plus RS, which is like 8 divided by 5008, which is very small, right? Much smaller than 1. So which means that we cannot hear any signal. So we lose the signal and we cannot hear anything on the speaker. So this is going to be a disappointment for you. You cannot listen to loud music. But when you have the audio amplifier, it behaves like a buffer. So it matches this music player with the speaker. Maybe it's not going to provide any gain, but it provides impedance matching and it can drive low load resistance, and therefore it's going to help. So this audio amplifier can be modeled by this drawing. R out, R in, AV times V in, like a two-port network, okay? In fact, any amplifier that you design, any amplifier available in the market can be modeled by these 3 simple components, 2 resistors and 1 dependent source. I will show you some more examples later on, but any amplifier, how many transistors that you have, that doesn't matter. Eventually can be modeled by this simplified version, simplified model. Anyway, when you put it in here, of course, it will look like this. On this signal are out. And the idea is you want to transfer whole Vs to the load. So you want to hear a very loud music, right? So you don't want to lose any extra information in here. So to be able to do that, of course, you want to make this Rin infinite, right? As high as possible. Why? Because then Vin will be directly equal to Vs. If Rin is infinite, you are not going to lose any signal on top of Rs. Similarly, you want Rout to be 0 because you don't want to lose any signal on Rout. You want to convert all this output on top of the speaker or the load. So in that case, Rs should be low, Rin should be high or infinite. And similarly, of course, you want Rout as low as possible, maybe 0 if possible, and RL to be high. But keep in mind that as a designer, you have control in this block. You don't know what kind of music player the customer will use. Therefore, you don't know what will be RS. And you don't know what type of speaker the customer will use. So you don't have any control on RL. Maybe he is using a low resistance speaker. Maybe he is using a high one. So you don't have any control on RL and RS. What you can control is only this box as a designer. Therefore, in fact, this is not an option for you. You cannot play with RS. You cannot play with RL. You can only control RIN of your own amplifier and the ROUT of your own amplifier. Okay. We will see more information about this thing later on, but I think this explains what is an amplifier, how you can model it, and when you are designing it, like there are some requirements like frequency, input resistance, output resistance, or the gain level. So when you take a look at the model, look at this model, RIN is critical, ROUT is critical. Of course, you want high voltage gain if possible. And besides that, what you want is, of course, the operation frequency should be compatible with the desired operation frequency. So when you take a look at the amplifiers, there are 4 main types depending on the unit of the gain. The voltage amplifier, input is voltage, output is voltage. So this is input, this is output, and the unit is volt per volt, or it's unitless, you can say. For the current amplifier, input is current, of course, output is current. Again, the gain is amperes per amperes, and it's unitless. But in some applications, input can be voltage, and the output is current. You want to supply voltage to the system or the amplifier, and you want to get current. And then, of course, the gain has a unit of conductance, right? Output amperes divided by input voltage. And the name comes from there, comes from the unit. So the unit is conductance or mho. That's why we call it as transconductance amplifier. Similarly, in another application, for example, you may want to use current as the input, and you want to get output as voltage. And output divided by input unit will be ohms or resistance, and that's why we call it as trans-resistance amplifier. These are the 4 main amplifier types, and we will learn how to design them throughout this course. But first, let's deal with input resistance and output resistance requirements for this type of amplifiers. For the voltage amplifier, the same story. We have control in this box. And even if you use many complicated transistors and circuits inside, eventually this amplifier can be modeled by these three components: gain, output resistance, and input resistance. And source is at the control of the customer. Load is at the control of the customer, so you cannot control RL and RS. So in this system, if you want to write the gain, voltage gain, there's one resistor voltage division in here. There's another resistor voltage division in here. And by using simple math, you can write V out divided by Vs as Rin divided by Rin plus Rs times RL divided by RL plus Rout times, of course, AV. And the goal is you want to maximize this whole term. So to maximize at the transistor level, you put some effort to maximize this AV. That's reasonable. But while doing this thing, you need to maximize this term and this term as well. And both these terms are less than 1, of course, right? But you can make them very close to 1. How you can make it? Keep in mind that you don't have any control on RS and RL. You cannot play with them. You can only change Rin and Rout. So how would you choose Rin and Rout to make this thing as high as possible? Of course, Rin should be much larger than RS. You want to make Rin infinite if possible. If it is infinite, this is going to be 1. But if you cannot make it infinite, you make it much larger than RS, okay? So Rin should be high or much larger than RS. Similarly, if you take a look at this part, if you make Rout 0, this term will be 1, maximized. If you cannot make it 0, then make it low or much less than RL. Okay, so this is the requirement for a voltage amplifier in terms of input resistance and output resistance. Let's take a look at the current amplifier. Now, we have a similar model, but keep in mind that input is current now, so the source resistance should be in parallel. Dependent source is current source now, so the output resistance should be in parallel. Why? Because it comes from basic 201 knowledge. If you have a current source, resistance in series is redundant. Why? Because, independent from this resistance value, the current passing through this branch is constant. There is no loss or change. So this is redundant. But if you put the resistance in parallel, then, of course, the current passing in this branch is different than this branch because this internal resistance is stealing some of the current. So the output current is different than the supply current. So that's why you model source resistance in parallel for current sources. For voltage sources, if you put the source resistance in parallel, again, this is redundant. Why? Because the value of the resistance or the source resistance does not change the potential across these two branches. But when you put the resistance in series, of course, for a voltage source, then you start having some voltage across this resistance, and because of that, output voltage will be different than the source voltage. This internal resistance is stealing some voltage from the actual voltage source. So by keeping this in mind, you have to revise the model depending on what kind of input you are using or what kind of output you are using. And the same story, in this box, you have the control. Actually, this is very complicated with transistors or whatever, but eventually you use like 3-component model: input resistance, output resistance, and the dependent current source. And if you try to write I out divided by IS, or the overall gain, there will be like some resistive current division over, and it can be written as RS divided by Rs plus Rin times Rout divided by Rout plus RL times AI. Again, the idea is you want to maximize the overall gain. In the transistor level operation, you play with this AI and maximize it. But in this term, you have only control on Rin and Rout. Rs and RL are fixed by the customer. So, of course, to make this term much close to 1, you want to make Rin 0 or as low as possible, Rout infinite or as high as possible. So Rin should be low or 0, which means much smaller than Rs. This should be high, much larger than RL. Look at the result. This result is completely opposite of what we had previously. For a voltage amplifier, you want Rin high. For a current amplifier, you want Rin low. The same story for the Rout. So depending on the type of the amplifier, your design requirements for input impedance and output impedance may change. Let's take a look at the other amplifier type, transconductance amplifier. Transconductance amplifier means that unit of the gain should be conductance. So output is current, input is voltage. So at the input, I am using a voltage source, series resistance. At the output, I am having a current source, parallel resistance. So when you write the expression, again by resistive divisions, you can write it like Rin divided by Rin plus Rs times Rout divided by Rout plus RL times the transconductance gain, and the unit is amperes per volt, and it should be consistent all the time. So in this case, to make this thing much close to 1, you want high Rin and you want high Rout. So both of them should be high as possible. So this is a different story than the previous one. So for transconductance amplifiers, you need both high input resistance and high output resistance. Maybe we are repeating ourselves over and over, but let's solve this last example. Trans resistance amplifier. Trans resistance means that output is voltage, input is current. So at the output, I'm using a voltage source with series resistance. At the input, a current source with parallel resistance. If you write the expression, that will be Rs divided by Rs plus Rin times RL divided by RL plus Rout times the transconductance gain. And of course, you can see that both Rin and Rout should be as low as possible. Moral of the story, depending on the amplifier type, you need to choose the proper input resistance and output resistance for your own design. Okay, so I'm going to talk about a different thing in here. So let's say that, let's go back to our previous example, the radio receiver. At the input, we had like 10 microvolt. At the output, let's say that you are using like 100-watt speaker. If you back calculate this thing, if it is 100 watt, power is V out cap divided by 2 RL. This means that the signal in here at the output is like 40 volts. So for such a system, look at the gain. You start at like 10 microwatt and you come to 40 volt. So the overall gain will be in the range of like 40 divided by 10 to the power minus 6, which is like 4 times 10 to the power 6. This is a huge gain, volt per volt, of course. Huge gain. So representing these large numbers is a bit difficult. So because of that, people introduced dB notation. Most of the time in dB, it's going to be equal to 20 log AV. So it will be something around like something larger than 120 dB. So it simplifies. So dB notation simplifies to handle large numbers in amplification, and people use it a lot. So for current gain again, we can do the same thing. AI dB is equal to 20 log AI, okay, and this one. And when you deal with the currents in here, of course, like there's a huge current gain in here. So you start with some I in here, you get some I out. If you use some typical values, the output current amplitude is like 5 amperes, but at the input you have current in the range of microamperes. Again, the current gain is huge. Sometimes people are giving the whole gain in terms of power. So let me find an empty spot in here and write it down there. Maybe I can write it in here. So AI is huge. I said we can use AI dB. AV again huge. We can use AV dB in dB notation. And keep in mind that it's going to be 20 log A. For power, it's a bit different though. Power gain is represented by 10 dB. APdB is 10 log AP, where AP is AI times AV. So you can find the power gain by multiplying current gain with voltage gain. But in dB scale, since you are taking the square because of AI and AV, you just use 10 log AP by definition, okay? So these are two important things. And one last thing, when we are dealing with these amplifiers, we assume that amplifier is linear. So let's say this is our amplifier. When we say it is linear, it means that if you have a sinusoid, sine omega 1t, you get a similar sinusoid but amplified version, sine omega 1t. So the gain does not change the frequency. Or in an extended way, if you have like summation of sinusoids, vi sine omega it, at the output you get the same thing but multiplied by a gain. So gain is frequency independent for linear amplifiers. Linearity means that all the frequencies are amplified in a similar way. Of course, this is not practically true. So what you do is you design this amplifier, take a look at its response at different frequencies, and we will do it in the coming lectures. And you take a look at the region where the amplifier is linear, and you want the customer to use the amplifier in that specified region for linear operations. So linearity is a given thing for us throughout this course. Unless otherwise stated, we will assume that the amplifiers are linear, which means that they amplify the signals with the same amount for all frequencies. But we will see that this is not true when we are dealing with low frequency and high frequency response later on. So I'm going to stop here for the first lecture. And in the second lecture, we will continue with design of single transistor amplifiers like this one. See you on next lecture.